All right, let's talk about one of Python's most powerful and kind of magical tools, the dictionary. We're going to pull back the curtain and see what makes them work with what feels like impossible speed. Seriously, have you ever stopped to wonder why Python dictionaries are just so ridiculously fast? I mean, you can have a dictionary with millions of items, ask for one thing, and bam, it's right there, instantly. How does it even do that? And then there's the other side of that coin, right? The dreaded key error. You try to get something and it just instantly fails. Well, it turns out that that lightning fast success and that instant failure are deeply connected. So the answer to both, the incredible speed and the sudden errors, is this really powerful idea called hashing. It's the secret sauce not just for dictionaries, but for sets too. So what exactly is it? Okay, so what is hashing really? Well, you can think of it like a super special converter. It takes any key you give it, like a word or a number, and runs it through something called a hash function. And what always comes out the other side is a number, a unique number that acts like a secret address. It really boils down to these four simple steps. First, you take your key. Let's say it's the word name. Second, Python applies that hash function. Third, you get a number. And fourth, and this is the magic part, that number points directly to a specific spot in your computer's memory, a spot we call a bucket. All right, so I just threw a new word at you. Bucket. What in the world is that? It's not a real bucket, obviously. It's just a really helpful way to picture how your computer organizes information. The best way to think of it is like this. Imagine a huge, long shelf with tons of little storage bins on it. Each bin is a bucket. The number from the hash function tells Python exactly which bin to go to. That's where it's going to store your key and its value. Okay, but wait a second. This brings up a pretty big question, right? What happens if two totally different keys, let's say the words apple and banana, go through the hash function and, just by chance, end up with the exact same number? Do they fight over the same bucket? Yeah, that can definitely happen. And it has a name. It's called a collision. And you know what? Python totally expects this to happen. It's built for it. When a collision occurs, Python just calmly says, okay, this spot is taken. And it just probes or looks for the next empty bucket nearby. It handles it all for you behind the scenes. So you're probably thinking, hold on, if Python has to go looking for another spot, isn't that going to slow everything down? And yeah, you'd be right. It absolutely could. But Python has this really clever strategy to make sure that hardly ever happens. The secret is that Python plays it smart. It keeps that whole big array of buckets, the hash table, intentionally sparse. That means most of the buckets are empty on purpose. By leaving all that open space, the chances of two keys colliding are super low. And if they do, finding another empty spot is no big deal. And this right here, this is the big trade-off. It's a huge design decision that the creators of Python made. See, keeping all those empty buckets ready and waiting uses up more of your computer's memory. But in exchange for using a bit more memory, you get that incredible speed. It's summed up perfectly in this one line. Python trades memory for speed. And for almost everything you'd want to do, that blazing fast performance is totally worth it. Okay, so that explains the speed. But hashing also answers another one of those big Python rules you just have to learn. Why do dictionary keys have to be immutable? Why can you use a string as a key, but you can't use a list? It all comes back to that hash value. See, Python only calculates the hash for a key one time, the moment you add it. That hash gives it the permanent address. Now imagine if you could change the key later, like adding a new item to a list. Its hash value would totally change, and Python would be lost. It would go to the old address and your data would be gone. The link would be broken. That's why keys can't change. And what's really cool is that this hashing magic isn't just for dictionaries. It's also the secret engine behind another amazing Python tool, the set. Sets are incredible for finding unique items and checking for duplicates in an instant. So how do they work? Think about it. A set is basically just a dictionary with no values. It's only the keys. It's a hash table under the hood. So when you add an item, Python hashes it and sticks it in a bucket. If you try to add that same item again, Python hashes it, goes to the exact same bucket, sees it's already there, and just ignores it. It's a brilliantly simple and fast way to guarantee everything in your collection is unique. So to really drive home just how mind-blowingly fast this is, let's put it all in perspective.
How does finding data with a hash table stack up against, say, finding something in a plain old list?
This is everything. If you're looking for something in a list, you have to go one by one, checking every single item until you find it. In a more complex structure like a tree, you have to walk down different branches. But with a hash table, nope. You don't walk, you don't scan, you calculate the hash, and you literally teleport straight to the data. It's a fundamentally different game. So let's wrap this all up. The big idea here is that hash tables, the engine in your dictionaries and sets, are unbelievably fast. And it all boils down to three key things. 1, they use that hash to teleport right to your data. 2, they keep themselves sparse to avoid collisions. And 3, they need those keys to be immutable so that the destination of the teleporter never ever moves. So I'll leave you with this. The next time you type those square brackets next to a dictionary name, remember what's really going on. You're not just retrieving a piece of data. You are commanding a teleporter, giving it the exact coordinates it needs to zap across memory and bring back what you asked for in the blink of an eye.